Hello, everybody. So today we're going to move into Chapter 5, Section 2, and you should have finished up your student loan packets. And so we're going to continue with our discussion of exponentials and show you some uses of what that log button is for on your graphing calculator or scientific calculator. So this is going to discuss logarithmic functions and what their graphs look like. So the first thing that I need to show you is what an actual logarithm, or what the definition of a logarithmic function is. And what you see here is in an equation, y equals log base a of x. And what that says is that is true if and only if x is equal to a to the y. Now, this is a formula that shows you how to take something from what we call logarithmic form and put it into what we call exponential form. This is one of the fundamental rules of working with logarithms. It's a really important concept that we will use a lot, which is why it's the first thing that I'm showing you. But it shows you how to take something from, as I said, logarithmic form, which is this, LF, and puts it into exponential form over there. And what you need to notice about this, if I erase this, when you're going from logarithmic form, you can see the base of the log right here is a. Well, the base of the log becomes the base of the exponent. That's the first thing to notice. So if you kind of look over here, we have a, it looks like a to the x, and we end up with a to the y. So that's how I remember that. The bases stay the same, so the base of the log becomes the base of the exponent, and then the x and y switch. And so that's how to go from logarithmic form to exponential form. Now, it is read as log base a of x. Now, why are we learning this? Well, in order to be able to solve logarithmic equations, you're going to need to know how to go from logarithmic form to exponential form. And so here's a couple of examples that I want to try. And you can see here's a function right here, and they want us to plug this number 32 in for x. Then we have a function here. They want us to plug the number 1 in, and so on. So I'm going to show you how to use that property to solve. So here's our first example. You can see we have f of x equals log base 2 of x. And they want us to evaluate this function when x is 32. So the first thing we do is put 32 in for x right there, and we get this new equation. And so the way that would be pronounced is f of x equals log base 2 of 32. Now, the way we can solve this is we can take this from logarithmic form and put it into exponential form. The first thing we're going to do is we're going to replace f of x with a y variable. Very simple. And then we take it from what is logarithmic form right here, and we will put it into exponential form. So it's pretty easy when you catch on to this. You can see right here, here's logarithmic form, here is exponential form. So the 2 is the base of the log, it becomes the base of the exponent. And then the 32 and the y switch places. So we end up with 2 to the y is equal to 32. And that's what we have right here. 2 to the y is equal to 32. And that comes from what I have underlined when you go from logarithmic form to exponential form. So one more time, take the base of the log to this power equals 32. So 2 to the y equals 32. And now what you see is we have an exponential equation that we should be able to solve using, if you recall from a few videos ago, your one-to-one property. We need to rewrite 32 so it has the same base. So 32 is 2 to the 5th. Now that the two bases are the same, you can see that y is equal to 5. And there's our final answer. Y is 5. So here's another example of a problem just like the first one. We have a function, f of x equals log base 3 of x, and x equals 1. So we will substitute 1 in and get our new function. Now that we've substituted 1 in, we will convert this from logarithmic form into exponential. In order to do that, we will replace f of x with y and then convert it. So it's this base 3, to the y power equals 1. And that's what I wrote right here. 3 to the y equals 1. Now, following that, we need to solve that. And what you should have realized is that anything to the 0 power is 1. Therefore, if y was 0, we would get 1. That means y is 0. And there's part B. Part C is similar. We have a function f of x equals log base 4 of x. They would like us to substitute the value of x equals 2 into the equation, which we do. Then we replace f of x with y. So we end up with an equation that just has an x and a y now. And we need to solve this. So how we are going to solve this is we will take it from logarithmic form and we will put it into exponential form using that same formula that I showed you. So the base of the log becomes the base of the exponent. So that 4 becomes the base of the exponent. And then the 2 and the y switch places. So it's 4 to the y power is equal to 2. So you can see I wrote that right here. 4 to the y equals 2. Now, once again, in order to solve, we need to have the base numbers be the same. So I can rewrite 4 as 2 to the second, which is what happened right here. So 4 becomes 2 to the second. And now we're left with a power to a power. So 2 times y. That gives me 2y. Once we have those two multiplied, you can see now that the bases are the same. And so we just set the powers equal to each other. So 2y is equal to 5. And solving that by dividing both sides by 2, you get y equals 5/2. And there's your final answer. Now, the last one I'm going to show you, I think, is a little trickier than the other ones. And it has to do with the exponent that we end up with. So once again, we start with a function. This time we have f of x equals log base 10 of x. And our x that we're substituting is 1 over 100. So substitute that in. Change f of x into y, just for ease of working with this equation. And now we can use the formula, or not really formula, but a property of a logarithm to rewrite this from logarithmic form into exponential. So the base of the log is 10. So it's 10 to the y power is equal to 1 over 100. And that's what we have right here. 10 to the y equals 1 over 100. Now we need to get a way to get the bases to be the same. And this one's a little trickier than the other ones because we have this 1 over 100. How are we going to do that? Well, 100 is 10 to the second power. It's the first thing you need to realize. So we're going to substitute 100 right here, and we put in 10 to the second. Now, after we have 10 to the second there, we need to bring it up. So it's at the top of that fraction. So when we bring that up, when we bring this 10 to the second up, it becomes 10 to the negative 2 power because we brought it from the bottom of a fraction up. Now that we have the bases the same, they're both 10s, we can set their powers equal, y and negative 2. So y is equal to negative 2, and that is your final answer for that one. So these are exercises using the different power properties and then utilizing this rule of a logarithmic equation and how to put it into an exponential form. Very important formula. Now, as a side note, if you have a logarithmic function with a base 10, it is called the common logarithmic function. It is typically denoted just by log. So if you look at the key on your calculator, it says log. That is log base 10. If the base of the log is different than 10, you have to use a different formula, which I will show you in a subsequent video. But for right now, understand that if you just see the word log, it is understood to have a 10 there. They may or may not write the 10 there. If it's not there, it's still a 10. It's just not written. So these ones ask you to evaluate the function f of x equals log of x at each value of x. So I'm going to pull up my graphing calculator, and we'll take a look at that. So the first one, they asked us to do log of 10. So your log key is right here. It says log. Type in 10 and close your parentheses. Then hit enter. You can see log of 10 is 1. Now, if I want to take log of 1/3, you must use parentheses when you have the 1/3. If you don't, it will only take the log of 1 and then divide that answer by 3. So you need to do log of 1 divided by 3. And you can see I get negative 0.477. The next one, log of 2.5. Once again, press the log button, 2.5. Hit enter, there's your answer. Now the last one I want you to notice, if I try to take a log of negative 2, and I hit enter, I end up with getting error, non-real answers. So what they're saying is you will get an imaginary number, non-real answer. So if you go to that, it's going to put the cursor right after the negative 2. So what that's telling you is that you actually cannot take the log of negative numbers. And the reason is it'll be more obvious whenever we take a look at the graph of a log function. But before that, we need to look at some log properties. Now, in the next few sections, I'm going to be giving you quite a few log rules that you will need to know how to use in order to solve various logarithmic or exponential equations. And there's quite a few log rules. In fact, what I normally do is have students take an index card and write all of those rules on the index card so you have it as a handy guide or a reference as you're working with these. You will be able to look at that and determine which formula you need to use. So it is important for you to keep in mind that we're going to get quite a few of these log rules. And if anything, you should at least have a little piece of paper where you've written these all down so you can automatically refer to that one piece of paper and have them all in the same place rather than trying to be flipping through your book or flipping through your notebook to find which rule that you need to use. So this first property is showing you the zero property. And what it says is if you have log of 1, doesn't matter what the base is. The base can be anything. But if you are logging the number 1, you will always get 0. And the reason it is always 0 is because of what I showed you the first rule, which is how to take something from logarithmic form and to put it into exponential. The base to this power equals the 1. So a to the 0 power is 1. Okay. Next one. Anytime the bases are the same, if you have log base a of a, as in, for instance, if I had log base 2 of 2, that always equals 1. Anytime the base matches the number that's being logged, you will get an answer of 1. And the reason, again, goes back to converting that from its logarithmic form into exponential form. And so a to the first power is equal to a. A to the first is a. That's what they're showing you right there. Now, the next one we're going to take a look at is what happens when you have a log where the base of the log matches the base of an exponent. And this is a very useful rule. What it says is if you have log base a of a to the x, that will equal just x. So as an example of that, if I had, get rid of this for a second, if I had log base 4 of 4 to the 6th power, that is simply equal to 6 because these cancel. The log base 4 of 4 cancels, just equals 6. That's called the inverse property. The last property I'm going to refer to today is the one-to-one property. And what that says is if you have log base a of x and that equals log base a of y, then you can say x and y are equal to one another. So log base a of x equals log base a of y, then x equals y. All right, so let's apply some of these properties. Okay, so number 3 says, use the properties of logs to simplify the following. And you can see we have 3 different problems, A, B, and C. Now, right here is a justification to the answer. But I scribbled out where the answers actually are because we need to figure that out. So if you look at the first one, it says log base 4 of 1. So remember, it does not matter what the base is. If you take log of the number 1, it will always equal 0. So the answer here is 0. And that comes back to that first rule that we learned right there. Anytime you log the number 1, it is equal to 0. So that's pretty simple. Next one, we have log base square root of 7 of the square root of 7. So if you recall, in one of the properties I showed you, if the base matches the number that is being logged, the solution is 1. So right here, these cancel, those are the same, equals 1. Okay? Now the last one is a little bit trickier. You can see we have 6 to the power of log base 6 of 20. Since the base of the exponent matches the base of the log, all of that cancels out, and we're simply left with the number 20. So there are 3 examples of problems that you can solve utilizing the rules of logarithms. Now, the next set of example problems I'm going to show you wants you to use the one-to-one property to solve. And the one-to-one property tells us that basically you've got to have the bases of the log be the same. And if they are the same, then what is being logged is equal. So if you look here, we have log base 3 and we have log base 3. So those are the same, which means then if these are going to be equal, x has to equal 12. Now, the next one is not quite as straightforward. We have a log right here, and we have a log right here. Now, you can see, as I said a little bit ago, since there is no base written, that is log base 10. So both of these have a base of 10, which means they're both matching. But what that means is, since these are equal, then these 2 things have to be equal. This has to equal this. So we will set that 2x plus 1 is equal to 3x. When I subtract 2x from both sides, I get x equals 1. And that one's solved. Now the last one's going to be done the same as I did the first 2. We check, that's log base 4. This is log base 4. So we know the log bases are the same. So now we will set x squared minus 6 equal to 10. In order to solve this, I will add 6 to both sides. I get x squared equals 16. And then when I square root both sides, I get x equals plus or minus 4. Okay, that's what I have for you today. As always, if you have any questions, feel free to email me. Have a great day.